Welcome to Talk Tensors. I'm your host, and today we are taking a deep dive into something that I really think fundamentally changes the way we have to look at large language models. We are moving away from the idea of a model that just, blabs out the next word and moving towards something that actually contemplates what it's going to say before it says it.
Yeah, it's great to be here. And you're completely right. This is a major pivot point. We're looking at this breakthrough called Quiet-STaR. And the core tension here, the thing we really need to wrap our heads around first, is the difference between how you and I talk and how a standard, GPT-style model talks.
Right, because when I'm talking to you like I am right now, I might pause. I might say, or there might just be this split second of silence where my brain is racing ahead, planning the sentence, checking if I'm about to say something stupid, and then I speak.
Exactly. And in cognitive science, we often call that system 2 thinking. It's slow, it's deliberative, it's logical, it consumes energy.
You do it when you're solving a math problem.
Or planning a complex argument. But current large language models, the ones we use every single day, they are impulsive improvisers. They are pure system 1. They see a sequence of words and they immediately predict the next token. Boom, boom, boom.
Just flying blind?
Yeah, there is no pause. There is no silent contemplation at all.
They're essentially just falling forward into the sentence.
That is a perfect analogy. They're falling forward. And usually they're graceful enough that we don't really notice.
Because they've seen the internet.
Right, because they have seen so much text, they can improvise a poem or a standard email without thinking. But when they hit a hard logic problem or a complex reasoning task, that impulsiveness causes them to hallucinate.
Or just completely fail.
Because they haven't planned out the logic steps required to get to the answer. They're trying to solve a math problem in the exact same rhythm they used to write a sonnet.
And that's the fundamental flaw, isn't it? You can't improvise a mathematical proof. You have to structure it. You have to think. So the tech we are covering today on this deep dive, Quiet-STaR, it's trying to give these models that pause. It's trying to give them an inner monologue.
Yes, but with a twist. It's not just asking the model to show its work, like we've seen with chain of thought prompting.
Oh, right, where you prompt the model to think step by step, and it just vomits out a massive paragraph of reasoning into the chat window.
Which is annoying, frankly.
I don't always want to see the sausage being made. If I ask a quick question, I don't want an essay on how it got there.
Exactly. And honestly, it's computationally inefficient to output all those tokens to the user anyway. Quiet-STaR is about architectural changes that allow the model to think between every single line of text it reads on the internet.
Every single line.
Every single one. It is teaching itself to reason on the fly, using completely unstructured data.
That is the part that just completely blew my mind when we were prepping for this. We aren't just training it on SAT questions anymore. We are turning the entire internet into a reasoning training ground.
Yeah, that's a big shift.
So, okay, let's unpack this. Because to really understand Quiet-STaR, we first have to understand what came before it. The loud star, I guess.
The predecessor is a method simply called STAR, which stands for self-taught reasoner. This came out a little while ago, and it set the foundation for everything we're seeing now.
So how did the original STAR work?
So STAR was a really clever way to bootstrap reasoning. You take a model, and you give it a data set of questions where you know the answer, like math problems or common sense questions.
Okay.
You ask the model to answer the question, but you also force it to generate a rationale, a chain of thought, before it gives the answer.
Okay, so it's like a math teacher saying, I don't just want the answer, I want to see the steps.
Right. Now, here's the trick. The model generates an answer. If the answer is wrong, we throw it away.
Because the reasoning was probably garbage.
We assume the reasoning was flawed, yes. But if the answer is correct, we assume the rationale, the steps it took to get there, was also good. So we take that rationale and we feed it back into the model as training data. We basically say, good job, do more of that.
Oh, that's smart. It's self-reinforcing. It filters its own thoughts based on whether they got the right result at the end.
Precisely. And it works very well. But there is a massive limitation here. It creates what we might call a data wall.
Because you need the answers.
Yes. STAR relies on supervised data sets. You need to know the correct answer to verify if the reasoning was valid.
And I'm guessing there are only so many math problems with verified answers in the world.
Exactly. High-quality reasoning data, like curated logic puzzles, math proofs, Q&A sets, it's incredibly scarce. It's expensive to make. Humans have to sit down and write it.
But look at the internet.
Right, the internet is an ocean of text. Books, articles, code, conversations on forums, but it's unlabeled. We don't have an answer key for a random paragraph in a sci-fi novel.
If I'm reading a mystery novel, there isn't a teacher standing over my shoulder saying correct when I predict who the killer is on page 50.
Right, and this is the key insight of Quiet-STaR. When you read that mystery novel, you are reasoning. You're reading between the lines.
How do you mean?
Well, if a character walks into a room and sees a wet umbrella, you immediately infer it's raining outside. The text doesn't say it is raining, but your brain fills in that logical gap to make the next sentence, he shook off the water, make sense.
Oh, wow. So reasoning is implicit in all text, even if it's not a rigid math problem.
It's implicit in almost all written human communication. The goal of Quiet-STaR is to generalize that old STAR method. Can we teach a model to generate those unstated steps, the thoughts about the wet umbrella, explicitly but internally?
To make it predict the why so it can better predict the what.
Yes. And that leads us to the quiet part of the name.
Because it's not spitting it out into the chat window.
Exactly. The reasoning is generated. It is used to inform the model's prediction of the next token. And then, crucially, it is discarded from the final output. The user never sees it. It happens quietly in the background.
It's like the model has a subconscious now. It's having thoughts that it doesn't share, but that shape what it says to you.
That's a great way to think about it.
Okay, I really want to get into the nuts and bolts of this because the engineering here is just fascinating. They break it down into 3 distinct phases in the source material: think, talk, and learn. Let's start with think.
The think phase. This is where the engineering gets really heavy. The challenge is obvious. If we want the model to think after every single word it reads, that is computationally incredibly expensive.
Yeah, if I have to stop and write a full paragraph of thoughts for every single word I speak to you, I'm never going to finish the sentence. It would take me an hour to say hello.
And for a computer, if you did that sequentially token, pause, generate thought, next token, pause, generate thought, it would be intractably slow. Training would take centuries. So the engineers proposed a solution called token-wise parallel sampling.
Parallel meaning it's doing it all at once.
Yes. This is a bit mind-bending. Imagine reading a sentence. Instead of pausing after each word to think, the model initiates a thought process for every single word in the sentence simultaneously.
Wait, let me try to visualize this. So if the sentence is, the cat sat on the mat, it's generating a thought branching off a thought branching off cat, a thought branching off sat, all at the exact same time.
Exactly. In one single forward pass of the model.
How is that even possible?
They achieved this using a very clever attention mask. Specifically, a diagonal attention mask.
Okay, let's unpack that. I know what attention is in a general sense. It's the model looking back at previous words to get context. But how does a diagonal mask help here?
In a standard transformer architecture, attention allows tokens to look back at previous tokens. By manipulating this mask diagonally, they create a setup where each token position can generate its own stream of thought tokens.
Separate streams.
Yes. These thought tokens can see themselves and they can see the preceding text of the main sentence. But, and this is the vital part of us, they don't see the thoughts being generated by the other token.
Oh, it's like a multiverse.
It really is. It's like having a separate conversation, branching off every single word at the same time. You're spinning up parallel timelines of thought.
So the thought stemming from cat is happening in a totally separate universe from the thought stemming from sat. There are parallel tracks that don't interact.
Exactly. And this is crucial for efficiency. You get to generate thoughts for the entire sequence in roughly the same time it takes to process the sequence once. You aren't stopping and starting, you're just widening the pipe.
And how does the model know, okay, now I'm thinking versus now I'm talking. How does it distinguish these parallel universes from the main timeline of the actual text?
They introduced meta tokens, learned tokens. There's a start of thought token and an end of thought token. These act as strict delimiters.
I found a little piece of trivia about this that I absolutely love. Do you remember how they initialized those tokens?
I do, yes. They initialized them using the embedding for the M dash, the long dash symbol.
Which is so poetic because in literature, an M dash is often used for a pause or an aside or a break in thought. So they basically told the model, hey, this token means what an M dash means. And that gave it a head start on understanding the concept of a break for thinking.
It's a brilliant heuristic. It biases the model towards pausing or aside semantics right from step one. Instead of starting from random noise and hoping the model figures out that this token means pause, you give it a nudge. You say, treat this like a parenthetical aside.
So that's the think phase. We have these parallel thoughts running. We have this multiverse of reasoning. But now we have a problem.
Right. The problem is that early in training, the model is dumb. Or rather, it doesn't know how to think yet.
Right, it's a blank slate.
So these thoughts it's generating are probably just random noise or complete garbage.
It's like asking a toddler to explain quantum physics. The thought is just going to be babble.
Exactly. If you just let the model rely on those garbage thoughts immediately, its performance on the main task predicting the text would tank. It would get confused by its own nonsense.
It would start hallucinating even more because it's listening to a corrupted internal stream.
Right. So how do we stop the model from listening to its own bad advice? This brings us to the talk phase.
The talk phase introduces a component called the mixing head, right?
Yes. Technically, it's a shallow multi-layer perceptron, or MLP. Think of it as a gatekeeper. Or better yet, a confidence slider.
Like a volume knob on a stereo.
A volume knob is perfect. The mixing head looks at two things. First, it looks at the prediction the model would make without the thought, the impulsive system 1 prediction.
The default guess.
Right. Second, it looks at the prediction the model would make using the new thought it just generated in the parallel timeline.
And it decides which one to listen to.
It outputs a weight, a mixing weight. It evaluates and says, okay, this thought seems totally irrelevant, so I'm going to set the weight to near 0. We're going to stick with the base prediction.
It mutes the thought.
Exactly. Or it might say, hey, this thought actually clarifies the context. Let's dial up the weight and use the thought influence prediction.
This is huge because it allows for a smooth transition. At the start of training, the mixing head basically keeps all the thoughts on mute.
Yes. It ignores them completely.
Yeah.
But as the thoughts get slightly better, the mixing head learns to trust them a little more. It ramps up reliance slowly. It's what we call a residual connection for reasoning.
Meaning it falls back on the safe option?
It ensures that thinking never makes the model worse than it started, which is a major stability requirement for training any neural network.
It's like learning to ride a bike with training wheels. The mixing head is holding the bike steady, using the base prediction, until the model proves it can balance and reason on its own.
That's a really great way to put it. It solves the cold start problem. If you forced it to use the thoughts from day one, the model would collapse into gibberish. This way, it only uses the thoughts when they earn their keep.
So we have the think phase, which is the parallel generation, and we have the talk phase, which is the mixing head volume knob. Now we need the learn phase. And I have to be honest, this is the part I struggled with the most.
It's definitely the most complex part of the system.
How do you teach it? If we are using the open internet and there is no correct answer key, how do we reward the model? How does it even know if a thought was good?
This is the crux of the whole technology. In the original STAR, good meant you got the math answer right. Here, good is completely redefined. A thought is good if it makes the future text more predictable.
More predictable. Okay, so let's go back to your mystery novel analogy.
Sure.
If I'm reading that novel and I think to myself, the butler did it, and then 3 pages later, the butler confesses,
then your thought was good. Because when you finally read the confession, you weren't surprised. Your internal model had already assigned a high probability to that outcome. The perplexity, which is the machine learning measure of surprise, was very low.
But if I thought the alien did it and the butler confesses,
then you were very surprised. Your thought led you astray. The future text had high perplexity. So the model learns to minimize surprise in the future text by generating better thoughts now.
But wait a minute. If the model just wants to predict the very next word, usually that's pretty easy. If the sentence is the United States of Bran, you don't need a complex philosophical thought to predict America. It's rote memorization.
Wow.
System 1 can handle that blindfolded.
You've hit on a key nuance that the engineers had to solve. They realized that if they just rewarded the model for predicting the very next word, it wouldn't encourage deep thinking. It would encourage trivial thoughts.
Like thinking is hard, let's just guess the easy word.
Exactly. So they need to reward it for predicting stuff further down the line. They call this non-myopic scoring.
Non-myopic meaning not short-sighted.
Right. They use a technique called teacher forcing to look several steps ahead.
What exactly is teacher forcing in this context?
It means we feed the model the ground truth of the future text and ask, how well did your previous thought help you predict this entire next phrase or sentence? Not just the next token, the whole phrase.
Oh, I see.
They measure it carefully. Did this thought help me predict the semantic content of the next chunk of text? If the thought made the complex, difficult tokens appearing later in the text more probable, it gets a positive reward.
That makes perfect sense. It's checking if the thought provided context that pays off in the long run. It's an investment. I'm going to spend compute thinking now so that I understand the paragraph better later.
And there's one more critical detail here to reduce noise. Because the internet is chaotic, right? They generate multiple rationale candidates, multiple different thoughts, and they compare them.
Like a focus group of thoughts.
Yes. They generate, say, 3 different thoughts for a single token. They compare the performance of each one in predicting the future text. They reward the ones that perform better than the average of the group.
Why compare to the average?
It stabilizes the learning signal. This is basically a variance reduction technique for the reinforce algorithm.
Reinforce is the specific machine learning algorithm they use for the reward.
Yes. It's a classic reinforcement learning algorithm. It's basically trial and error. I did X, I got a reward, I will do X again. But reinforce is notoriously unstable.
It jumps all over the place.
Exactly. By comparing against the average, the baseline, they make sure the model is climbing a steady hill, not jumping off cliffs randomly.
So it's competing against itself, thought A versus thought B. If thought A helps predict the next sentence better than the adage, thought A gets a gold star.
Precisely. And this loopthink, talk, learn, runs over massive amounts of web text. They use data sets like Open Web Math and C4. It's reading Wikipedia, it's reading math forums, it's reading news. And slowly, it learns that thinking helps it understand what it's reading.
It's incredible to think about this running on massive clusters of GPUs, just reading the web and whispering to itself, slowly getting smarter over weeks of training.
It's a very elegant system.
So let's talk results. Because this all sounds great in theory, but does it actually make the model smarter? Or does it just make it slower?
It definitely makes it slower, which we'll get to in the limitations. But yes, it unquestionably makes it smarter. And the results are genuinely impressive because of how they were achieved.
Break down the setup for us.
They took a Mistral 7B model, that's a standard high-quality base model, and they trained it with Quiet-STAR. Then they tested it on GSM-8K, which is a benchmark of math word problems, and Common Sense QA.
And to be abundantly clear for everyone listening, they did not train it on GSM-8K or Common Sense QA.
Zero. None. They did not show it math problems with answers to train it. They just let it read the internet and practice its silent thinking.
This is the zero-shot capability everyone in the industry always talks about.
Correct. The model had never seen the test format before.
What were the actual numbers?
On GSM-8K, the zero-shot performance went from 5.9% to 10.9%.
Okay, 10% doesn't sound like a passing grade for a human taking a math test, but for a machine of this size.
You have to look at the relative improvement.
Yeah.
That is nearly doubling the performance. Doubling it just by learning to think on unstructured web text. On Common Sense QA, it went from 36.3% to 47.2%.
That is wild. It got better at math simply by learning to think while reading random news articles and Wikipedia pages. It suggests that the structure of reasoning is universal.
That is the big philosophical takeaway here. Reasoning isn't just a math thing, it's a language thing. By learning to predict the flow of arguments in web text, argument A, therefore argument B, the model learned structures that transfer directly to solving algebra word problems.
It essentially learned the shape of logic.
Yes, and it learned that taking time to generate intermediate steps improves accuracy across the board.
Did they see a correlation with the length of the thought?
Yeah.
Like, if it thinks longer, is it smarter?
They did. Performance consistently increased as the length of the internal thought increased. More tokens to think resulted in better answers. It's a direct validation of the hypothesis that more compute time, more System 2 effort, yields better intelligence.
This reminds me of that idea in recent AI chatter about test time compute, that we can trade compute for intelligence dynamically.
This is exactly that, but baked into the pre-training or fine-tuning stage. It's not just a prompting trick you do at the end, it's the model's native behavior.
I also found the distribution of utility section of the analysis really interesting. You mentioned earlier that it doesn't need to think for the United States of America. Did the data actually bear that out?
It did. They call it the heart token phenomenon. Quiet-STAR helps disproportionately with difficult-to-predict tokens. The mixing head, that volume knob we talked about, it learned to shut off thinking for the easy stuff.
It learned to be lazy when it could be.
Or efficient, depending on how you look at it. Why burn GPU calories thinking about the word the? But for information-dense tokens, the mixing head cranked up the volume. There was a specific example in the research involving chemistry that I loved.
Yes, the magnesium example. Walk us through that. It was so cool.
So the text the model was reading was describing a chemical reaction. It started with mentioning magnesium. Then, the text was about to describe the next step in the procedure. For a standard model, guessing the next step based just on the word magnesium is hard. There are a million things you can do with it.
Right. You could burn it, dissolve it in an acid, throw it in a lake.
But the Quiet-STAR model generated an internal thought. The researchers peeked inside the black box and saw the thought it generated. It retrieved knowledge about magnesium nitride. It thought to itself, magnesium reacts with nitrogen to form magnesium nitride.
And it didn't output this text to the screen.
No, it kept it entirely quiet. But that unstated piece of knowledge helped it predict that the next step in the text involved heating the magnesium in a nitrogen atmosphere. It bridged the gap between the concept of magnesium and the procedure of heating.
That is exactly what we want these models to do. We want the model to pull relevant background info that isn't explicitly stated in the prompt. It's like having a knowledgeable expert who doesn't show off, but just gives the right answer based on deep context.
It connects the dots, and it does it autonomously.
But of course, it's not all sunshine and rainbows. We have to talk about the limitations. This isn't a free lunch. If it was, everyone would be doing it already.
No, it is certainly not a free lunch. The most obvious cost is literal cost. Inference overhead.
Just the raw compute power.
Generating thoughts adds tokens. Even if you hide them from the user, the GPU still has to compute them. It makes the forward pass significantly heavier.
So if you're running a startup and paying for compute, this makes your API calls more expensive and much slower.
Yes. They mention that parallel sampling helps during training, but during inference, when you're actually using the model to chat, if you want the benefit of the thought, you have to wait for the thought to be generated sequentially. You are trading time for intelligence.
So the user experience changes. Instead of instant streaming text, you get a loading spinner while the model ponders.
Exactly. And for some applications like real-time translation or voice assistants, that latency is unacceptable. For others, like drug discovery or legal analysis, it's totally fine.
There's also the faithfulness problem. This one always bugs me with AI interpretability. Just because the model generated a thought that looks like logic, did it actually use that logic to get the answer?
This is a deep issue in the field right now. We can see the generated thought, which might say, since A is true, B must be true. And we see the final output, which is B. But we can't guarantee causal linkage inside the neural network.
It's just a black box.
The model might have just guessed B using its System 1 intuition and generated a thought as a post hoc justification, basically making up an excuse that looks like reasoning.
Like when humans make a gut decision and then scramble to find a logical reason for it. I ate the cake because I needed the energy for my workout.
Exactly. We're teaching the model to mimic the appearance of reasoning that leads to good predictions. We hope that requires actual reasoning, but neural networks are notorious for finding shortcuts. It might be generating reasoning-sounding noise that somehow triggers the right answer in the upper layers without actually being formal logic.
It's faking it till it makes it.
And we can't always tell the difference.
And what about bias? The analysis touched on this, and it seems like a real double-edged sword.
This is a subtle but dangerous one. If the model learns to reason by reading the open internet, it learns the logic of the internet.
Oh no, the logic of the internet is not always sound, to put it mildly.
Right. If the internet contains biased reasoning, stereotypes, fallacies, motivated reasoning, the model might learn to internalize that as valid logic. If thinking like a biased person helps it predict the text written by a biased person, the reward function will say, good job.
So if it's reading a highly polarized political forum, it learns that if X happens, blame Y. And it internalizes that logical leap.
It amplifies the bias.
Yeah.
Because it's not just mimicking the words anymore, it's mimicking the thought process behind the bias.
Mm-hmm.
It's optimizing for predictability, not truth. If a conspiracy theory forum has a specific internal logic, the model will learn to replicate that logic to predict the next post on the forum.
That is deeply concerning. But technically, it's doing exactly what it was asked to do. It's predicting the text.
It is. It's a very faithful mirror of the data it consumes, which reinforces the need for better data, not just better architectures.
There was also a note about technical instability in the training process, something about reinforce being a total nightmare to manage.
Reinforce is notoriously unstable as a training algorithm. That has very high variance. And here you're combining it with a moving target. Remember the mixing head?
The volume knob.
It's changing its weights at the same time the thoughts are changing. So the gatekeeper is changing the rules while the thinker is trying to learn the game.
That sounds chaotic. How did they even get it to converge?
It is chaotic. The researchers noted they had to avoid complex value functions like you'd see in PPO, proximal policy optimization, because it just fell apart. They had to stick to a simpler reward structure to keep the math from exploding. It shows that we are really at the bleeding edge of what we can stabilize in training.
It feels like we're trying to balance a pencil on its tip while the table is shaking.
That's a very fair description of advanced RLHF and these new reasoning techniques. It works, but it's incredibly delicate.
All right, let's pivot. We've covered the what and the how. Now I want to get into the what if. It's time for our novel notions segment.
Let's do it.
This is where we take the tech we just discussed and extrapolate wild ideas. As a disclaimer for you listening, this is for entertainment purposes only. Don't build your startup on this without checking the physics first. I've got one ready to go.
Lay it on me.
The subconscious API.
Ooh, okay. I like the name.
So right now, Quiet-STAR generates these thoughts, uses them, and then discards them. They are completely ephemeral. But what if we expose them? What if we built a glass box mode?
Go on. How would that work in practice?
Imagine a medical diagnosis bot. You type in your symptoms. The bot replies with, "You probably have a viral infection. Take some rest." Standard output. But via the subconscious API, it streams a secondary text channel directly to the doctor.
And that channel contains the quiet thoughts.
Exactly. It shows the doctor, patient mentions headache and fever, ruling out meningitis because no neck stiffness, considering flu, considering COVID, probability of bacterial infection low based on symptom timeline.
That is incredibly valuable because right now, AI in medicine is a black box. We get the answer, but we don't know if it considered the dangerous alternative and ruled it out, or if it just forgot about it entirely.
Right. It turns the black box into a class box. It doesn't change the user interface for the patient, but for the expert supervisor, it provides the differential diagnosis. It reviews the context that led to the decision.
It connects back to that faithfulness limitation we discussed earlier. If we expose the thought stream, we can audit it. We can see if the reasoning is sound or if it's hallucinating logic. You could have automated auditors checking the thought stream for fallacies.
Exactly. It's like telepathy for AI. You can read its mind while it talks to you.
I like it. It's totally plausible. The tokens are already there, being computed. We just need to pipe them out. Well, I have a notion that flips the script on the economics of this whole thing.
Okay, let's hear it.
Dynamic compute pricing, or as I call it, the thought meter.
The thought meter.
So we talked about the mixing head. It's a confidence slider. It knows when the model is struggling and needs to think and when the text is easy.
Right.
Currently, we pay for AI by the token. Input tokens, output tokens. It's a flat rate. But Quiet-STAR shows us that not all tokens are created equal. Some require massive compute, lots of internal thoughts, and some require almost none.
So you're saying cloud providers should charge us based on how hard the model had to think?
Exactly. Dynamic allocation. Imagine a cloud provider charging by cognitive load. If I ask the model, what is 2 plus 2, the mixing head stays at 0. Low compute, cheap, fractions of a cent.
But if I ask it to derive a novel proof for a quantum physics problem,
the mixing head screams, I need help. The model spins up 100 parallel thought streams. It effectively slows down to think hard. And the price for that answer reflects the massive compute spike.
it's like Uber search pricing, but for artificial neurons.
And it enables thought ensembling. You could have a slider as a user, I'm just chatting, versus I'm making $1 million business decision. If you slide it to high stakes, the model forces the mixing head to generate 1,000 parallel thoughts and vote on the best one before speaking.
I love that. I'm feeling lucky versus I need to be right. It turns intelligence into a utility with variable voltage.
And it solves the latency problem. You only pay the latency cost when the problem actually demands it.
That is a fascinating future, a world where AI doesn't just output text, but contemplates it first, and we pay for the quality of that contemplation.
It really moves us from language models to reasoning engines.
Yeah.
And Quiet-STAR is the first real proof of concept that they can teach themselves to do this on the open web.
Well, on that thoughtful note, I think we are going to wrap up. This has been a fantastic deep dive into Quiet-STAR. We've gone from impulsive improvisation to quiet contemplation. Something for you to ponder on your own. If a model learns to think by reading our internet, what kind of thoughts is it going to have about us?
That's a slightly terrifying thought to end on.
It's a step towards machines that don't just speak, but actually understand. Thanks for listening to Talk Tensors. Keep thinking.
See you next time.